Hello everyone, I'm Frank and welcome to Frank Puzzles, and this is today's hard level difficulty puzzle. And it's called Two Truths and a Different Truth by Oddly Even. And here are the rules. We have normal Sudoku rules apply, which means put the digits 1 through 9 once each into every row, column, and box. We have yin-yang, where we need to shade some cells in the grid such that all shaded cells are orthogonally connected and all unshaded cells are orthogonally connected. And no 2x2 area may be all shaded or all unshaded. So this is a valid yin-yang shading because what it means to be orthogonally connected is, as a region, is that every cell in the shaded region must be able to get to any other cell in the shaded region just by going through edges, all while staying within the region. So for example, to get from here to here, it just has to go all the way around here, all going through cells, all staying within the region. And it's the same thing for the unshaded cells. All the unshaded cells can go to any other cell in that region just by going through edges, all staying within the region. This would not be valid because obviously then this cell could not get to the rest of the unshaded cells by going through edges, all while staying within its region. And this section, even though they can get to each other by going through edges while staying within the region, they cannot go to any other cell that's in this outer region here, or in this outer region here, just by going through edges while staying within the region. They would have to go through a corner or exit its region. And this would also not be a valid shading because this 2x2 area is all shaded now. So is this. So that is not valid. And so that's how yin-yang works. And an example of how yin-yang works. We also have doubler's rule set, where a cell that is a doubler has value equal to twice its digit. So say, for example, this was a doubler. Then this would have to have, if it were a 6, it would have a value of 12. So that satisfies that. So that's an example of how doublers work. We also have, and this is actually something you need to, or not pay attention to. Hopefully I'll explain it well here. This is two truths and a different truth. Where, for all of the following constraints, if shaded cells are treated as doublers and unshaded cells are normal, then 2 of the clues are correct and the third is incorrect. Oh. And if unshaded cells are treated as doublers and shaded cells are normal, then the same 2 clues are incorrect and the third is correct. Okay. So, okay, I'll give you a little, I don't know, sort of draw back the curtain behind this. I actually tried this one out earlier. I did not understand this rule. I thought that we had to determine whether the shading was doublers or the shading was non-doublers. But it's actually both. So, say this was the actual shading of the puzzle. It's not, but I'm pretty sure it's not. But say this was the shading of the puzzles. When, actually it shouldn't be if the shaded cells are treated as doublers. It should be saying when shaded cells are treated as doublers and unshaded cells are treated as normal, then 2 of the clues are correct and the third is incorrect. If the unshaded cells, when unshaded cells are treated as doublers and shaded cells are normal, then the same 2 clues that were correct in the previous ones are now incorrect, and the third one is correct then. So that's what it should be saying. It should be when shaded cells are treated as correct, not if. Because the problem is with the if, I was like, wait, so that means we don't know if shaded cells are doublers or not. They could be doublers or they could be not doublers. It should be, so okay, part of it is that the wording isn't quite precise enough. It's good, but the problem was I didn't understand because it said if. It shouldn't be if shaded cells are treated as doublers. It should be shaded cells can't have to be treated as doublers in one instance, and they have to be treated as non-doublers in another instance. And you have to do both. Otherwise, it doesn't make any sense. You can't solve this puzzle. And I was trying to solve this puzzle for not a decent, it was about 15 minutes. And then I'm just like, I don't know how to approach this. And the reason was because I was stuck on if shaded cells are treated as doublers. But we know, so I was looking at the example, it's more that when shaded cells are treated as doublers and unshaded cells are normal, then two of the clues are correct and the third is incorrect. When shaded cells are not treated as doublers and are treated as normal, and unshaded cells are treated as doublers, then the same two clues which were correct earlier are now incorrect, and the third clue that was incorrect earlier is now correct. So it should be when shaded cells are treated as doublers, not if, because that was throwing me all off from that, basically. Because you have to treat the shading both as in one scenario as being doubling and as another scenario as not being doubling. Otherwise, it doesn't make any sense. And I was being stuck there and I couldn't figure out even how to approach this. So, we know then that the shading stays the same. You have to treat it once as the shading is doubled, and then once as the shading is normal, and the unshading is doubled. And in that instance, in the instance where you treat the shading as doubled, then two of the clues, of the following clues, which is Renban arrows, X dots, and odds and evens, are correct, and one is incorrect. Then when you treat it the opposite way, with the shading as normal and the unshaded cells as doublers, then you have two. The two clues that were correct become incorrect, and the clue that was incorrect becomes correct. Okay, that makes a lot more sense then of how to actually approach this. It's still not, like, for me, it's still I'm trying to still figure out how to approach it. But I spent 15 minutes just basically staring at this and going, how the heck do I approach this? And I couldn't figure it out. And now it makes a lot more sense. So anyways, let's get to the rules where we have to have two correct and one incorrect. On a Renban, values on the pink line form a set of consecutive numbers with no repeats. So, for example, say this was the actual shading here. Then this could be something like 2 and 3 and 5 and 7 here. So the values of these would, assuming the blues are doublers, and then this is correct. This would be 5, a value of 5, a value of 2 doubled, which is 4, a value of 7, and a value of 3 doubled, which is 6. So this would form essentially a Renban values of 4, 5, 6, and 7, which forms a set of consecutive numbers with no repeats. So that's an example of how Renban lines work, if it's correct. Again, so if all the Renban lines are going to have to be correct in some context. That is the point. That is, I guess, the point. Oh, that's actually very interesting. Huh. Anyways, I have to think more about that. We have arrows, where values on an arrow sum to the value in that arrow's circle. So again, say this was actually correct. Then this could be something like, let's remove these numbers. We could have 3, 2, 1, and then this is 1. And this would have to be an 8. Because the sum of the values on the arrow would be 2, which is 1 doubled, plus 3 plus 2 plus 1. And this is assuming that the blue is double. The shaded cells are doubled right now. But this would be 2 in value plus 3 plus 2 plus 1, because these are all non-doubled. They're normal. That would add up to 8, which is this value not doubled, right? Oh, that's fascinating. Huh. Anyways, so that's an example of how arrows work. Say we had values on an x sum to 10. Say, again, the blue was doubled. So you could have something like 2 and 6 here, and this would add up to 10, because 2 doubled is 4 plus 6 is 10. And this would satisfy that rule with the doubler. Again, it has to... The blue is doubled in one scenario, and it's not doubled in the other scenario, which you have to satisfy both of them. So that's an example of how X works. We also have dots, where values on white dots are consecutive. Oh, that's interesting. Values on white dots are consecutive. Values on black dots are in a 1-to-2 ratio. So, assuming this, again, the blue... Actually, let's this time assume white, the non-shaded, was doublers. If this is 3, this would have to be 5 or 7. Because, again, we're using, now, this time, the white cells as doublers. So this value would be 6, which is consecutive only with 5 or 7. And again, the blue values are non-doublers in that case. And then values on a black dot are in a 1-to-2 ratio. So say, for example, this was 2. This would have to be 1 or 4 to maintain the 1-to-2 ratio between them. And that works either... Oh! That tells me something about that. Interesting. Okay, we'll get to that when we start solving. And then finally, we have odd and even. Oh, that's interesting. Where the value on a gray circle is odd, and the values on the gray square are even. Huh. Okay, I'm seeing something there too. So again, for each of these, the red band arrows, X, dots, and odd and evens. Dots, you have the white Kropke dots and then the black Kropke dots, because those are going to be distinctly different rules. So when the shaded cells are basically considered doublers, 2 of the clues are going to be correct, and then 1 clue is going to be incorrect. Then when you have the shaded cells not as doublers, and then the unshaded cells are doublers, then the 2 ones that were correct are no longer correct, and the one that was incorrect has to be correct now. So that is how all the rules and how this works. Hopefully I explained it well so that you can understand and don't get into the same situation where I was trying to solve an unsolvable puzzle, where basically the shading stays the same. We have to evaluate the puzzle in where the shaded cells are in the doubler and the unshaded cells are normal state. And we also have to evaluate the puzzle where the shaded cells are a normal state and the unshaded cells are a doubler state. And in the prior one, in the first scenario where we evaluate it, 2 of the rules are correct and 1 is incorrect. In this latter scenario, we have those 2 that were correct in the first scenario are incorrect now in the second scenario. And the second one in the latter scenario has to be incorrect. Sorry, it has to be correct in the second scenario. So the one that was incorrect in the first scenario is now correct in the second scenario. Hopefully this all made sense. Anyways, those are all the rules. If you'd like to play along, there's going to be a link in the description. And now I'm going to get started. Let's go. Okay. What I just thought of. The black dots are in a 1-to-2 ratio. But they have to be incorrect at some time. So that means you cannot have a correct ratio in both situations, which means that you have to have the doubling effect affect every single one of these scenarios. It's not a problem for the white Kropke dots, but for the black Kropke dots, if they were both the same shading, then they would have to be correct. If they're correct in one scenario, they're correct in the other scenario too, right? If you have 1 and 2 as a normal 1-to-2 ratio, and then you try to double both of them, there become 2 and 4, which is still a 1-to-2 ratio. So this cannot be the same shading here, because if they were, the problem is that basically they would always maintain the 1-to-2 ratio no matter what, and they have to be incorrect in some scenario, whether with the shading changes their form essentially. So these have to be different shadings. This has to be different shading. So this has to be different shading, this has to be different shading, and this has to be different shading. We also know the odd and even digits have to be odd sometimes, because they have to be, in the circle case, correct sometimes, and in the square case, they have to be incorrect sometimes. So to be, that means you're guaranteed to, in one of the states, to be odd. So that means these have to have odd digits in them to be odd, right? And then they have to be essentially in some sort of scenario where they basically work. That's interesting, especially with this black Kropke dot. What does that mean? Well, obviously, it can't be double of itself. I think I know what this has to be then. Okay. It can never be 5, 7, or 9 here. Because if it's 5, 7, or 9, you're just never gonna, if you double it, that's 10, and that would be in a 1-to-2 ratio only with 5, which we already have a 5 in the row here, right? Or in the box, however you want to put it. So that works for 5, 7, and 9, right? If this is in a 1-to-2 ratio, say we double this value. First of all, 5 can't be normal in a 1-to-2 ratio with any other digit. And that also works because of doublers too, right? If you have a doubler, 5 would only be next to 5 doubled, 7 would be next to 7 doubled, and 9 would be next to 9 doubled at the only way. But you can't have that because they would be in the same row or column. So that's not possible. So, because of this, that means this can never be 5, 7, or 9. Well, what about 1 and 3? Well, the problem is these have to be different regions. Because you have, you can't have them both be the same region because they would always just maintain the 1-to-2 ratio between them. So this is not possible to be 1, 2 or 3, 6. So essentially, it has to be. So where can they be in a 1-to-2 ratio? I think the only one is 1 doubled. It can be in a 1-to-2 ratio with 4, right? If you try to have 3 doubled, that's 6, and you don't have 12 as a digit, as a single digit. And then, right, so you can't have obviously 3 doubled next to 6 doubled, because then that doesn't work either. So I think it has to be here. This is 1 doubled next to a 4. Right? So 1 doubled in value. This is a single value. This is a normal value. This can no longer be 1. I think the only scenarios where you can have are 1 and... you could have 2 with something too. So, in yin-yang shading, once you swapped twice, you can never swap again. So this has to be all the same shading. We're going to mark it as blue. And then this must be the same shading. So this is green. So that means these two must be even. Wait. That means I think this is green. I like to use blue as shaded and green as unshaded. It technically doesn't matter, but I like to do it just for not memorization, but just it makes sense to me, right? Because blues tend to be shaded. It's a shaded color, sort of. But these match when they are both the same shading. And that's if shaded cells are treated as doublers, then the unshaded cells are normal, then 2 of the clues are correct. So these are only correct if these are both doubled. So therefore it must be shaded. Okay. So then these are shaded, which means both of these are all the rest of this is unshaded. And again, this is because in yin-yang shading, if you swap twice already, you can't swap anymore. And the reason, if you swap shading, you can't swap anymore. And the reason, let's just show an example. So say this was shaded and this was unshaded. How do you orthogonally connect the unshaded region without blocking the shaded region? You can't, right? So the blue can never form one single unshaded region orthogonally connected that way. That's why you know these are all unshaded. Therefore, that forces this to be shaded, this to be shaded, this to be shaded here. Therefore, we have 1 and 4. So obviously, if the blues are shaded, or blues are doublers, then this, and greens are normal. This is 2 and 4, which is in a 1-to-2 ratio. This would be 3, 5, 7, or 9 doubled, so they'll both be even. Therefore, this cannot be blue. If this were blue, then all 3 of them would be even, and that's not possible, so this must be green. That forces this to be blue here because of the 2x2 area is all unshaded so far. And that's why we have these corners of blue. This must be a corner of green here. This blue has to go out this way because there's no other way to go out. It can't go this way because it's stuck here. These are different shadings, so this must be green. So this goes this way. We don't know. Okay, so this is definitely shaded, or this is definitely an edge. This is definitely an edge. So is this, so is this, so is this. This blue has to get out, so this must be blue. The green has to get out, so it connects that way. We have a 2x2 area that's all green, so this is blue. That means this is shaded. This is that, and this is fixed there. This blue must go out here to connect. This is a boundary. Okay. How do we get 1 to 2 ratios with... Okay. I think you... Okay, so you can have 1 doubled with 4 on the other side. I think you could have 2 doubled with 8 on the other side. And those are the only ones that work, right? 3 doubled... Yeah. So this has to be a 2-8 pair here in some order. This has to be 1-4 or 2-8. Because 3 doubled is 6, and again, that doesn't jive with a single digit. And that's what these black Kropke dots have to be, right? One of them has to be doubled, which is a smaller version, which is in a 1 to 2 ratio with, which is, if you double it again, you get a single digit. And that's the way, so it basically is in a 1 to 4 ratio with these digits here. So the only digits that are in 1 to 4 ratios are 1 and 4 and 2 and 8. And the reason is because you need one of them doubled and then one of them not doubled and to be in a 1 to 2 ratio. But then in the other scenario where one is not doubled, the first one that was doubled was not doubled and the other one is not doubled being doubled, then that would have to be in a non 1 to 2 ratio. Okay. This can't be 1 and 4, so this must be a 2-8 pair. This is 1-8 or 2-4 here. We don't know which. Okay. This is all green. Because this is all green, the only time this is going to be correct is when they are non-doubled. And right, because if these are doubled, there's no way this can form a valid Renban. You'll have something that's like 6 times 2, which is 12, which we can't have a value of 11 here. So this has to be the valid when the shaded cells are doubled. So it's one of the two when it's valid. We also know 1 and 4 cannot be here in that scenario. So what does that mean for this then? So this is definitely valid when blues are doublers. And that means there are 2 of them when blues are doublers. This is guaranteed to be 1 or 4 here along one of these. So we have to have, okay, none of them are doubled. So it has to be either 1 through 8 or 2 through 9 here. 2 of these digits here one of them has to be 1 or 4. If we had a 1 here, this would be 1 through 8, and then this would have to be 9. But where would the 9 be? I guess it could be. So we are guaranteed a 2 through 8 here. 1 and 4 have to be some semblance here. Obviously, when this is doubled, this is not going to form a Renban. Okay. What else do we know? Hmm. We know at some time these guys have to add up to 10. Um, Obviously, if they're both doubled, they would no longer add up to 10. If you double both of them, they would no longer add up to 10. This has to be some sort of odd or even set. Does it? Actually, no. It could be like 1 or 3 doubled with 5. 3 doubled with 5 or 7, as I said earlier. Hmm. So we're not guaranteed that either. These 3 digits cannot be the same as these 5. So these 3 digits must be in this set that adds up to. Oh! Hmm. That doesn't tell us very much, though. Okay. If 9 is in one of these x's here, you have to have the 1 with it. Because 9 cannot add up to 10, and it's going to have to add up to 10 sometime. Whether when blues are doublers or blues are not doublers in one of the scenarios, you have to add up. So saying we had a 9 here, we are guaranteed then that the 1 has to be here then, if that's the case. So if this is 1 through 8, 9 has to be here, which means 1 has to be here, but then we don't have a 1 in value here, so this can't be 1 through 8. This has to be 2 through 9 in value. And it has to be when blue is the doubler and green is normal. So this must be 2 through 9, which means 1 has to be one of these. 1 could be with 9 here. We don't know. So we know 1 has to be one of these 4. So this 1 is guaranteed to be here. 4 cannot be here. This digit here and this digit must match these 2 digits. So this is guaranteed to be a 4 here. 1 is guaranteed to be here because we tried to have 1 through 8 here. That's not possible because we tried to have 1 through 8. That forces 9 to be here, which means 1 has to be here to add up to 10 sometime in some scenario. And 1 can't be here anymore. So then this can't be 1 through 8. So this has to be 2 through 9, which means 4's that way. 1 is guaranteed to be here. 1 doubled. So 1 as a normal digit could be with 9 or 8. We don't know which. This can't be 2 or 8. It has to be... Okay, so that's actually helpful. This can't be 1, 4, 2, or 8 because of the 2, 8 pair in the column. So this is 3, 5, 6, 7, or 9. That means this is 3, 5, 6, 7, or 9, so it cannot be 2 or 8 there. We know the 1 to add up to 10 in some scenario, it either is 1 doubled with 8 or 1 normal with 9. So 1 out of 8 or 9 is with this 8 1. We're not sure which. You could have 2 8, 3 7, 4 6. Can you ever have a 5 here? And I think the answer is no. 5 can never be in a scenario where it adds up to 10 with another unique digit, with a different digit, right? So 5 has to be one of these digits, which means this cannot be 5. That means this can't be 5 either. And 5 has to be one of these 4 digits here. So 5 is one of these 4. You have to have at least one odd in each of these white crocky dots, but we don't know which. Um, so again, y could be with 8. Sorry, 1 could be with 8. 1 could also be with 9. This has to be correct sometime. Okay, so you don't have access to 1, so it cannot be 1 through. So, So 2 of these are doubled on this Renban. Same here. 2 of these are doubled on this Renban, but this is more restrictive, so maybe let's look at this one. There are 2 doubles here guaranteed to be on this Renban. It cannot be 1 and 4. So I think this has to have a 2 and 3 doubled here. Which, if that's the case, 2 and 3 doubled would be 2 doubled is 4, 3 doubled is 6. It can't be 3, 4, 5, 6 because we're already using 3 doubled. 5 doubled is 10. Oh, 10 could work. Except that we need 4 doubled too to make that a Renban, and we can't have 4 doubled. So it has to be specifically 2 and 3 doubled on this Renban to work. And because we have 2 that are the same set shading and 2 that are the other shading. So you're going to have 2 guaranteed to be doubled in whichever scenario it's correct. And it has to be correct in one of those scenarios. So you have to have 2 doubled, 3 doubled. You can no longer have 3 as a normal digit. 2 doubled is 4, 3 doubled is 6, so we have to have the values 4, 5, 6, and 7. So this must be 3 or 7. That forms this to be 4 with 3 or 7 here. We have to have a guarantee 2, 3, 5, or 7. So if this is 3 or 7, that would mean, if this is 7, that would mean those aren't doubled. So the 7 would have to not be here. So again, the 7 and the 5s are the non-doubled ones. So when the 7 is non-doubled, that would mean 5 is non-doubled. The 3 and the 2 are the doubled ones. That means if this is 3, this would be 2. This 2, 3, 5, 7 quadruplet in this box 1 eliminates 2, 3, 5, 7 in the rest of the box. So this can't be 3, 5, or 7. It's 9. It also removes 2 in the rest of the box. So this is 8 and 2. Therefore, in the case of blue being shaded, this would be value 16, and this would be value 2. So this is not correct in that scenario, which means this has to be correct in that scenario. So therefore, this is 1 or 2 with 4 or 8 shaded here. Right? Because when the blues are doubled, 2 of the clues are correct. This is 16 to 2, which is not a 1 to 2 ratio. This is 2 and 4, which is a 1 to 2 ratio. So this would have to be either 1, which would be doubled, 2 to 4, which is a 1 to 2 ratio, 2 doubled, which is 4 to 8, which is in a 1 to 2 ratio. So this is 1 or 2 with 4 or 8. This is 2, 8, that's 9. That leaves the remaining digit here as a 6. Okay. This is 3 or 7 here. Okay. Hmm. So this digit here, well, it doesn't have to be that one. It could be here. Hmm. So 9 cannot be here. 8 can't be here. Interesting. So if 1 is here, it's with 8 doubled. If 1 is here, it's with 9 by itself. Huh. That's kind of fascinating. Um, this is at least a 6. It has to be valid sometime. So 6 plus 1 is at least 8, which is a minimum of 4 doubled. 4, 5, 7, 9, because it can't be 6 or 8 because of 6 or 8 in the row. Um, hmm. Huh. Okay. What else do we have? This is fascinating, actually. When I was trying to solve this previously, without that, you had it. The clues had to fulfill it during one scenario or the other. It was hard. It was. I just could not figure out a way to purchase to get to figure this out. But this is a lot easier, I should say. Um, oh, you're not guaranteed 1, 8, and 9. It could be 1 and no, 4 has to be here. Right. Yeah. 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 Yep. 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 So yeah, because 4 has to appear somewhere on this Renban, and it can't be here. These are all um, non-doublers, so they're normal cells. So that means you have to have a 4 normally. So that means 4 is guaranteed to be here. So therefore, this can't be 1 and 4 both doubled. Um, this could be 2 and 3 both doubled. It could be 2 and 8. Um, 3 and 7. 4. It cannot be 4 and 6. It could be 2 doubled with 6, though. 3 doubled with 2. No, that doesn't work. 3 doubled with 2 doubled. And obviously 4 double doesn't work. 5 double doesn't work. 6 double doesn't work. Hmm. Hmm. What else do we have? Oh, wait. This is at minimum. It cannot be 1 or 2. It has to be at minimum 3. Oh, so this has to be a doubled. This is at least 6, 3, and 1. That means this cannot be 4. It's 5, 7, or 9. Huh. Interesting. One of these two is blue, at least. One of these two is blue, at least. One of these two is blue, at least. Hmm. Interesting. Oh, let's make the edges not black. Let's make him red. Because it's hard to differentiate sometimes between those, right? But that's why I like using red, because it's much clearer about where the boundaries are. But still kind of tough here. Um, hmm. Oh, that's interesting. Can this be correct if these are doubled and these are not? I don't think so, right? It would have to have two odd digits. You'd have to have two odd digits, so this would not be doubled. This would have to be 1 and 3, and then these would be doubled. But you can't have one doubled here then, which would mean which we would have to have one here not doubled. So I think this has to be correct when blue is doubled. Right, yeah. So again, if we try to do it when blue is not doubled here, we know this Renban works when blue is the doubler. So we need another one when blue is not doubled. Sorry, when blue is doubled. So we're looking at this Renban, will it work when blue is not doubled? Because we want to prove that this has to occur when blue is doubled. That means when blue is not doubled, you have to have two odd digits in the non-doubled. So this has to be 1, and then it would have to be with 3, but then that would have to have a value of 2, which is doubled, which would be 1 doubled, but we already have a 1 in the box, so that cannot work. So if we have blue as doubled, I think 1 still doesn't work here, right? If we have 1 doubled, I guess it could work. You have to have a 2 doubled essentially here, is essentially what I think we're showing, right? If you don't have 2 doubled here, say you just have 1 doubled, that's a value of 2. This Renban cannot be 1, it has to be 2, 3, 4, 5. So if this is 1 doubled, it has to have 2 doubled here to form the evens, and then you have to have 3 and 5 here. If this is 2 doubled, I guess this could be 1 doubled with the same scenario. Or 2 doubled with 3 doubled. And if you have 2 and 3 doubled, that's 4 and 6. We can't have a 3, so it must be 5 and 7. So this is guaranteed to be 5 here. Where is the 4 in this box? It cannot be anywhere here because one of these must be 4 to satisfy the Renban when this is correct. And it is when it's not doubled. So 4 cannot be here. 4 can't be any of these. So this must be 4. So this has to be 4 and 1, which forces this to be 2. So this is 1 doubled, which is 2. 2 doubled, which is 4. We have to have a Renban here. We don't have a value 1, so it has to be 3 and 5. That eliminates 1, 3, and 5 in the rest of the box. So the rest of the box has to be 6, 7, 8, 9. Ooh, that's interesting. Anyways, so this 1-to-2 ratio, or this Renban works when the blue is doubled. This Renban works when the blue is doubled. So this Renban must work when the blue is not doubled here. So this must be a 7 then. And this must be 5. And these must be 2 and 3 doubled. When green is doubled, it works. Because this only works when blue is doubled. Yeah, so this 2, 3, so that means this becomes a 4, 7 pair here, which eliminates 4 and 7 in the rest of the column. This can't be 7. This is 6, 8, 9, which eliminates 6, 8, 9 in the rest of the box. So this is 7, which means this can't be 7 here. This only works when it's not doubled. Because when it's doubled, you're going to have, at minimum, 6 plus 8, which is 14, doubled, which is 28, which not a single digit, even doubled, can add up to. So this has to be blue. This is green. This already adds up to 6 plus 8 is 14, plus 1 and 2. So it has to be 6 and 8. 1, 2. Okay, so this 4, 7 pair eliminates 4 and 7 the rest of the row. Remaining, okay, so this can't be 6, 8, or 9. So this is 2, 3, 5. The remaining digits in row column 9 are 1, 2, 3, or 5. This can't be 2 because of the 2 in the row here. We're guaranteed one of these is a 1. This cannot be 1 here. So the 1 is with 8 here. So one of these is 1. So this one is with 8 here, or it's with 9. We're not sure which. Because it cannot be with 4 doubled. That's the only other possible combination to add up to 10. 7 has to be one of these. Okay, so this digit, 6 plus 8 is 14. So minimum 14 plus minimum of 3. That's 17. So this has to be 9 doubled. So this is going to be 9 here, which means 9 cannot be here. So 9 has to be one of these two. It cannot be 5. 1 is guaranteed to be part of this because you can only have 1, 2, or 1, 3 here. So this is 1, which means neither of these could be 1, and this is 2 or 3 to add up with. This has to be 6 guaranteed because 8 and 9 already add up to 17, and 1 plus 2 add up to 3. That's 20, which is more than 9 doubled. This has to also not be doubled, because if it were doubled, it just wouldn't work. We'd have 1 plus minimum 4, which is 5. 5 plus 14 is 19, which is greater than 18. So this is green, which forces this to be blue. So we have boundary here, boundary here. This is a 2, 3, 5 triplet, which eliminates 2, 3, 5 in the rest of the box. So that's 4, 6, 7, and 8. 7 cannot be here. 4 cannot be here. We are guaranteed one of these is a 7. Which can only be, these have to be the same set. That's the only way that's ever going to be consecutive. Because 7 could be with 2 or 3 doubled, but the 2, 3, 5 triplet eliminates that possibility. This can't be 5. So one of these 2 is 5. Well, we already knew that. Okay. This 2 eliminates 2 here, so this is 3, which makes this 5, which makes that 2. This 2 eliminates 2 here, so it's 3, which means this can't be 3. This can't be 2 because of the 2 in the column. This 3 eliminates 3 here, so it's 5 and 3. This adds up to 4, so this must add up to 14. So this is 6 and 8, which makes this a 9. This only works when blue is doubled. So these have to be the same set because it's not consecutive. The 7 is only consecutive. Yeah. And it has to be blue because this must go out here. And again, if these are opposite sets, that's never going to work. 7 is not going to be consecutive with 6 or 8 doubled. And then 7 doubled is not consecutive with 6 or 8, period. So this is blue. This is boundary here. This is boundary. One of these is going to be green. We don't know which. This can't be 5 anymore. Because of the 5 in the row. This 3 eliminates 3 here. Remaining digits in column 7. We have 2. 5 can never be here. Oh, this can't be 5 because of 5 in the column, so that forces this to be a 5 here. So this has to be 2. So it could be 2 doubled. It cannot be. It could be 2 doubled with 6 or 2 with 8. So this cannot be 6 or 8. Therefore, this is guaranteed to be 2, which makes this not 2. Okay, that seems fine. Remaining digits in row. So this is guaranteed to be 2 here. 6, 8, or 9's there. That's fine. This 1 eliminates 1 here. This 3 eliminates 3 here. Possible digits here. 3, 6. No 1, 2. It could be 3, 4, 6. No 5. 7, 8. No 9. Okay. Remaining digits in row 2. We have 1, 4, 5, 6, 7, 8. 5 again cannot be here. Remaining digits in row. Okay. Remaining digits in row 3. We have 1. Okay, this can't be 5. One of these two is a 5. We have 1, 3, 4, 7, or 9. So 1 can add up with 9. Okay, so 1 doubled would have to add up with 8. So 1 could be either of these. 1, 9, 1 doubled with 8. 3 and 7 work, but this can't be 7. Well, guaranteed one of these digits is a 3. Three doubled with 4 works. 3 with 7 works. 4 doubled with 1 doubled works. 4 and 6 works. 8 can never be here. 8 could work with 1 doubled. Never mind. That's fine. This, we know it can't be doubled. That's all we know. But we don't know if it's blue or green to match. Okay. What else do we have? Remaining digits in row 4. We have 1, 3, 4, 6, 7, 8. This can't be 4, 6 because of the 4, 6 in the column. I think that's it, right? 1 doubled could be here with 3. There's a lot of possibilities there. Anyways. Ah, this white dot works only when blue is not doubled. So that means these must work when blue is doubled and green is not doubled, right? Because if this is blue doubled, that's 14 as a 7, which is not consecutive with 12 or 16. So it has to be when blue is not doubled, this works. We don't know if that mixes. One of these then has to be green. One of these has to be green, but we don't know which. It could be both are green, right? Um, hmm. So that means we are guaranteed either this is 3 or this is 7, but we don't know which. Hmm. Okay. Remaining digits here. In column 2, we have 2, 3, 4, 6, 7, 8, 9. This can't be 2 in this column. This can't be 3. This can't be 3 or 9. This can't be 2. This can't be 4 or 7. This can never be 2. Can't be 2 doubled. Can't be 3 doubled either. So it can't be 2 or 3 here. Because it's at minimum 8. Mm. Six doubled is possible. Can this ever be? Hmm. Well, obviously, one of these three has to be at least blue. It could be all of them are blue, though. Interesting. Huh. Say this was green. If this is green, that forces blue to go here. This would then be 1. They would be different sets. So one has to be either doubled. No, one would have to be doubled. Because if you had 9 doubled with 1, that doesn't work. And then 9 and 1 would not be opposite of each other. So this would be 1 and 8. So that only works. Therefore, this would be 6. But the problem is this doesn't work if blue is doubled. And this doesn't work if blue is doubled. So therefore, this can never be green. This has to be blue. So it must be the same set, which means it's 1 and 9. So this is guaranteed to be 9, and that's 1. That eliminates 1 here. And this can't be 9 anymore. So this has to be 7. This is 7. This is 4. That's 7. This can't be 9. This becomes 9 here also. This can't be 4. This can't be 4 or 7. So this 7 eliminates 7 in the rest of the box and the column. These cannot be the same set because then that would be 2. Well, it could be. It could be 2 greens. Actually, this has to be green. Huh. Because this 2x2 area is all blue. So there's that. here, we have 1 and 3 with 4, 6, or 8. That's never going to add up to 10 unless the 1 and 3 is doubled. And we know 1 and 9 does not work, add up to 10 if they're doubled. So this must work when blue is doubled. This must work when blue is doubled. So if that's the case, then this is blue. This is diagonally across from each other. If we had green and green here, we would not be able to orthogonally connect the green regions and the blue regions. So this cannot be green here. This is blue. This green has to go out somewhere here, so this is green there. Therefore, they're the same. And again, they must work. They must add up to 10 when blue is doubled. So this is 2 and 8, which makes this 6. This can't be 6. These can't be 8 anymore. This is 1 or 3 doubled. And that has to add up with... Oh, shit. Oh, apologies for that. That doesn't work. Because this has to be blue also. Oh, it works as 1, 4. It works as 1, 4. Okay, so this has to be 1, 4. Woo! I was wondering, because this 2x2 area was basically problematic here. Because there's 3 greens here. But because this 1 and 4 works, that satisfies that. So these can't be... This is not 1, that's 3. So these can't be 4. It's a 5, 6 pair here. This can't be 1 because of 1 in the column. Cannot be 4 because 4 in the column. Can't be 3 because 3 in the column. This is 7. This is 14. So it has to be... Okay, if this were doubled, the problem with that is... And this was the same set. The problem with that is that this is minimum 10. This is minimum of 6. So 16 is never going to add up to 14 with another digit. So this must be the opposite. And these cannot be doubled because, again, that's 12 plus 5 at minimum if they were both doubled. So this is blue. If this were doubled, that would be 3 doubled at minimum. 12 plus 5 is 17, which is greater than 14. So this cannot be doubled either. So these all have to be blue. Again, this is a diagonal of blue. We have a 2x2 area of blue here, so this can't be blue. This is green. We have a diagonal here of blue. It cannot have a green across it, so this must be blue here. So we have boundary. Oops. How do I get orange there? Anyways, boundary there. This adds up to 14. So it has to be the minimum, right? Because the minimum adds up to 3, 6, and 5, which is 14, which is what exactly 7 doubled is. So this is 3, that's 5, that's 6. That eliminates 6 here. This 3 eliminates 3 in the rest of the row. So to satisfy this, I think it cannot be 1 doubled anymore. The odd digit for when this Kropke dot, white Kropke dot works has to be 7. 1 can't be with any other digit. So this is 7. And that's with either 4 doubled or 8 regular. So either of those works. This can't be 7. It's 1 or 8. This can't be 7. We have a 4, 6, 8 triplet, which eliminates 4, 6, and 8 in the rest of the row. So this is 1. This can no longer be 3 here. So this only works when greens are doubled and not blues. So this needs to work when blue is doubled then. Okay. That means we have a 1 here. This is at minimum 4 and 6, so this must be doubled. So that's blue. One of these must be doubled. Because otherwise, if they're both green, that would be a 2x2 area, which is all green. So one of them is doubled. Which means we need an odd digit here. So it's either 7 or 9 as the non-doubled. Can we ever have 6 doubled? 6 doubled would be 12 plus 7 and 1, which would be 20, which is greater than a single digit. So no, we can't have 6 doubled. We have to have the 4 doubled. This can't be 3. This 3 eliminates 3 here, so it's 2, which makes this 3. That eliminates 2 here. I think this has to be a 4 doubled. If we had, so say we had, can this ever be 9 as the non-doubled? 4 doubled is 8, plus 1 and 9 is 18, but that would force a 9 here, which is not. So this has to be 4 and 7 here, which eliminates 4 and 7 in the rest of the column. So the 4 is doubled here. One of them's green, one of them's blue. Because we can't have 2 doubled here. 1, so 1 and 7 add up to 8. 4 doubled is 8. 8 plus 8 is 16, which is 8 doubled. So this is 8, this is 6, that's 9. Which means this can't be 1, 3, or 9 because of 1, 3 in the column and the 9 in the box. So this is 5. Okay. This 7 eliminates 7 in the rest of the box. 1 can't be here or here, so 1 is one of these digits. 2 has to be one of these digits. 3 can't be here. 3 can't be here, so 3 is one of those 2 digits. Interesting. This is border. Remaining digits in box 4. We have 5, 6, 8, and 9. 8 and 9 cannot be here because of the 8 and 9 in the column, so this becomes an 8, 9 pair. That forces this to be a 5, 6 pair. Remaining digits in column 1. We have 1, 3, and 4. This can't be 1 because of the 1 in the row, no 4 because 4 in the row, no 3. And we have remaining digits in column 3 are 2 and 7. This can't be 2 because of the 2 in the row, so this is 7, which makes this 2. Okay, remaining digits in row 9. We have 1, 4, 7, 8. 7 cannot be either of these. Where is the 7 in row 9? It has to be here. So this is 7. Okay. Okay, this 8 eliminates 8 here. So this becomes a 6, 7 pair, which eliminates 6 and 7 in the rest of the box. This can't be 6. This can't be 6. We have a 4, 8 pair in row 4, which eliminates 4 and 8 in the rest of the row. So this must be 6. We have a 2x2 area that's all blues so far, so this has to be green, which has 3 blues, I should say, I guess. This is green. Okay. Huh. Okay. Hmm. Okay. Oh yeah, this is when blue is not doubled, so therefore this must be when blue is doubled here. So this must work when blue is doubled, which means this cannot be doubled, which means it's green. Since this is green and green, this has to be green across it, because if you had blue and blue, you would have to have one region that's split. So this is then working when blue is doubled. So this must be 7 and 8, which makes this 4, which makes that 8. That eliminates 8 here and 8 here. Where's the 8 in row 9? It has to be here, which eliminates 8 here. We have a 2-9 pair. Where's the 8 in row 1? It has to be here. Okay. So these are boundaries. These are across each other on the diagonal, so this cannot be blue here. This is green. This 2x2 area is this 2x2 area has 3 greens, so this must be blue. So when this is doubled, it is incorrect. So these must be green, I think, because of that. Right? If this is doubled and it's not satisfying the even or the odd digit in the circle. So therefore, these must be when blue is doubled. So these are odd. This is even. So this is green, which means this has to be green here because this diagonal is green. So this diagonal, one of these is blue, one of these is green. The blue has to extend out here to connect. We have a 2x2 area here, which is 3 greens, so this must be blue, which means these are diagonal blue, so this cannot be green. This must be blue. So we have boundary here, here, here. Okay, this must be satisfied when we have blue is doubled. So this cannot be blue because we need an odd digit here. So this has to be an odd digit. Cannot be 5 or 7. It could be 1, 3, or 9. But this is doubled. So if it were 1, that would not work. Cannot be 5 or 7 because of 5 or 7 in the row. 3 could be. It cannot be 1 doubled here. It could be with 2 doubled, though. 3 cannot be doubled here because 3 doubled would be 6, which is not consecutive with 3 or 9. So 3 has to be here. 9 could be, so 3 would be with 2 doubled. 9 would be with 4 doubled here. Okay. This 8 eliminates 8 here, so it's 6 and 8 here. This 5 eliminates 5 as a possibility there. Okay. Remaining digits in row 8. We have 3, 4, 5, 6. This can't be 3 or 5 because it's 3 or 5 in the column. This cannot be 6 because 6 in the columns can't be 3, 4, or 6, so that makes this a 5, which means this can't be 5. This becomes a 3, 4 pair in row 8, which eliminates 3 and 4 in the rest of the row. So that's 6. This is, so if this is 3, this is guaranteed to be 2 doubled. If this is 9, this is guaranteed to be 4 doubled, or it could be 5 doubled also. It could be 4 or 5. Okay, so that's not guaranteed there. Okay, well, that's fine. One of these two is a 5, so that's fine. Okay, remaining digits in column 6, it's 2 and 9, I believe, right? Yeah. This 2 eliminates 2 here, so this is 9, which makes that 2. This 9 eliminates 9 here, so it's 1, so this can't be 1 anymore. Remaining digits in box 5. We have 2, 4, and 5. This can't be 5 because of 5 in the column. This can't be 2 because 2 in the row. Where is the 1 in column 5? Can't be here, so it has to be here. None of these can work because of 1's in the boxes. Can't be either of these because 1 in the row, and this doesn't satisfy this parameter. So this is 1, that's 4, which makes this 3, which makes that 1. Remaining digits in row 7 are 3 and 9. This 3 eliminates 3 here, so it's 4, which eliminates 4 here, so it's 5. This can't be 4, 5. It's 2 doubled. 2 makes this 4. 2 eliminates 2 here, so it's 9 and 2. 2 doubled can be only consecutive with 3. So that's 3 and 9. This 8 eliminates 8 here, so it's 9 and 8. This 5 eliminates 5 here, so it's 6 and 5. 6 eliminates 6 here, so it's 7, 6. 7 eliminates 7 here. So this is 4, which is the doubled. So this is blue, which makes this green. The blue has to go out somewhere, so it has to connect to here. These are green across from each other, so that must be green here, which forces this to be blue here. And then this blue has to connect, so that's blue. And we have all of the... Whoa, what the heck was that? I don't even know. We should have all the shading. So the shading is the blue. And the green is the unshaded. So let's just check. For the Ren bands, while blue is doubled, this does not form a Ren band. 2, 3, 10, 14. This does 2, 3, 4, 5, 6, 7, 8, 9. And this should. So this is value doubled 1, 2, doubled to 2, 3, 2 doubled to 4, and 5. So 2, 3, 4, 5, which does satisfy that. Now, what happens when you reverse them? This is obviously the digits 2 through 9 doubled. So that's 4 through 18 even digits. This would be 7 and 5 not doubled, 2 doubled, which is 4, 3 doubled, which is 6. So 4, 5, 6, 7, which does form a Ren band. This would be 1 and 2 not doubled, and then 3 doubled, which is 6, and then 10, which is not a Ren band. So that's satisfied for the Ren bands. For the arrows, 3, 6, and 5 doubled is obviously not going to add up to 7. 4 doubled is 8 plus 1 and 7 is 16, which is 8 doubled. So that's satisfied there. 1, 3, 6, and 8. 4 plus 6 plus 8 adds up to 18, which is 9 doubled, which is satisfied there. For the arrows the other way, if blue is not doubled, 3, 5, and 6 add up to 14, which is 7 doubled. 4 plus 1 and 7 doubled, which would be 8, 16. That obviously doesn't add up to 8. And then 3, 1, 6, 8 doubled obviously does not add up to 9. Okay? X's, values on X sum to 10. For blue doubled, 1 and 9 does not doubled, adds up to 20, which is not satisfied. 1 and 4 doubled adds up to 10. That's satisfied. 2 and 8 are not doubled, so they add up to 10. And then if you 1 and 4 not doubled add up to 5. 2 and 8 doubled adds up to 20, and 1 and 9 not doubled adds up to 10. So this is the only one that satisfies it when blue is not doubled. Okay, dots. 1 to 2 ratio. When blue is doubled, this is 2 to 4, which is a 1 to 2 ratio. 16 to 2, which is not 1 to 2 ratio. And 2 to 4, which is a 1 to 2 ratio. When when blue is not doubled, 1 to 8, which is not a 1 to 2 ratio, 8 to 4, which is a 1 to 2 ratio, 1 to 8 again, which is not a 1 to 2 ratio. So that's there. The white dots, 6 and 7, when blue is doubled, this is 12 to 14, which is not consecutive. 7 and 8, which is consecutive. 4 and 3, which is consecutive. When blue is not doubled and green is doubled, this is 6 and 7, which is consecutive. 14 to 16, which is not consecutive. 6 to 2, which is not consecutive. So all the white dots are done. And then we have odds and evens, circles. When blue is doubled, this is 2, this is 3, that's 5, which means those two are odd. When green is doubled and blue is not, this is 6 and 10, which are not odd, and 1, which is odd. Even value of squares, when this is 2 and 18, which are both even, and this is 7, which is odd. When blues are not doubled, this is 1 and 9, which do not satisfy the evenness, and this is 14, which does satisfy the evenness. So this should be solving it, 7. And that's a solution. Still pretty hard puzzle, but definitely not as hard as when I originally was going through this and had read completely wrong, or I could completely misunderstood the rules. Very cool rule set, actually. I like it a lot. I just wish that basically it had been changed to when shaded cells are treated as doublers instead of if. Because if implies that it could be treated as doublers or it could not be also, right? That's the implication. It should be, though, treated as a doubler and also not treated as a doubler, but only in those situations, right? Anyways, I hope you enjoyed this solve, and I'll see you next time on Frank Puzzles. Take care.